So problem 11 and 12 from 2.6 are on the screen right now, and this is really getting pretty deep into the weeds. I'm going to do 11 with you. It has one new concept. It has to do with when a graph is horizontal as opposed to going down or going up. And if a graph is horizontal, we say the graph is constant in that region. Never would test on this. Doesn't even come up in my brief calculus class, but it could come up in a calculus class. So I want to expose you to it, but you're not responsible for it. We'll do it together. So I want to find the intervals where the graph is increasing, where the graph is decreasing, where the graph is constant, if there's a local maximum point and a local minimum point. I'm going to separate the graphs, and now I'm going to put a hard break right here. There's a period at the end of this graph. So my first interval is going to start at -5. It's not going to start at infinity because of the hard break, not having an arrow or an extended graph. And then I'm going to stop at what isn't actually a minimum point because it's not lower than the points to the right of it, but it's a point where the graph changes directions. It changes from going down to going horizontal. And then I have a region where the graph is horizontal. And then where it stops being horizontal and it starts going down. And then a region where it goes up. I need to make this my first interval, my second interval, my third interval, and my fourth. The region where it's going down, then it's flat, and then it's going down, and then it's going up. This first region I'm not starting at infinity because of the solid dot there, but I always do round parentheses. My first interval is going to go from -5, which is the x coordinate of that point, which is a maximum point, to the x coordinate of -2. That's not a maximum nor a minimum point. For it to be a minimum point, the graph would have to shoot back up. Since it's flat, this isn't lower than the point right next to it. So that point's not, it's a distractor point. It's not a maximum point. It's not a minimum point. My middle interval goes from the x coordinate where it flattens out, where it starts flattening out, to the x coordinate where it ends flattening out. And that's going to be -2 to 0. My middle interval where it picks up going down is going to go from this x equal to 0 to that x equal to 2. In the far right interval, I get an infinity because the graph is going on forever. It's going to start at 2 and go to infinity. And now I'm going to describe what the graph is doing. In this interval, my marker goes down. That's a decreasing interval. The second interval, my marker goes horizontal. That's what we call constant. I don't know if I can fit it in here. If the graph doesn't go up nor down, it's constant. The third interval, my graph is decreasing again. And the fourth interval, my marker is going up, so the graph is going up. Now I can answer the increasing, decreasing, and sneak the constant in, still all around parentheses. So first interval, it's not at an infinity because the graph doesn't go off to -infinity. First interval is a decreasing, and I put it in the increasing like a Dummkopf. So -5 to -2. Middle interval, -2 to 0, that's where it's flat. We call that constant. Third interval, which is 0 to 2, that's another decreasing interval. I put it in the decreasing. I have a second decreasing interval, so I put a U. Last interval, increasing because it's going up, and that's the 2 to infinity. So that's the increasing, decreasing constant part. This point, it's higher than anything close to it. There's nothing to the left of it, and the points to the right of it are lower. That's my maximum point. These are neither one are minimum points because the points directly to one side of them are not higher nor lower. This point down here is my minimum point. So when I go to answer my question, the coordinates of the local maximum point are -5, 7. The local maximum value is y equal to 7, which occurs when x equals to -5. and my minimum point, or my local minimum point, is the point 2, 0. The local minimum value is y equal to 0 when x equal to 2. So I'll make sure my answers are correct, because sometimes I write wrong answers down and that's a bad thing. My key's actually even wrong, but that's okay. Good. I'll skip 12. You're not responsible for constants or graph like this on the test. The next concept I almost didn't put in the class because it would just seem silly. If I give you a table of data, I have x's and then function notations for y's. I'm asked, does this table represent an increasing or decreasing function? I just look at the y's. If the y's are getting bigger, it represents an increasing function. The y's are getting smaller, it represents a decreasing function. This just seems silly. If I look at the y's in this first table, is the table representative of an increasing or decreasing function? Well, my y's go from 5 to 10, then 10 to 20, then 20 to 40, then 40 to 70. The y's are getting bigger. That's what it would be if I was showing points on the graph. This is an example of an increasing function, specifically because the y's are getting bigger. That's hardly worth the 10 seconds that I spent on it. Problem 16 asks me if this data represents an increasing or decreasing function. And as the x's get larger, the y's are getting smaller. That's what decreasing shows up as when you look at points. If the x's get bigger, the y's get smaller, the table is considered decreasing. And that's a semi-big deal that I kind of sloughed over. In this first number 13, I should have done 14. The x's were getting bigger and the y's are getting bigger. That's what increasing means. As the x's get bigger, the y's get bigger. Decreasing are as the x's get bigger, the y's get smaller. One more concept, and it has to do with graphs that don't go beyond to any of the infinities. If a graph is nice and tightened up, it has periods on the edges, no breaks between, then if that's the case, if we have a graph that doesn't go off to either infinity in either direction, it's bound with closed circles between, then we can pick out something called an absolute maximum and an absolute minimum. An absolute maximum is the absolute highest point in the picture, and for this, that point would be considered the absolute maximum. It's absolutely higher than any point. That point might be a local maximum. It's higher than the points next to it, but it's not absolutely the highest because that point is higher. This point down here, I would call the absolute minimum, specifically because there's no point in this picture that's lower than it. So the absolute maximum and the absolute minimum only apply to graphs that don't have any breaks in them and that are hard stopped on the left edge and hard stopped on the right edge. The absolute maximum is the point that's higher than all the other points. The absolute minimum is the point that's lower than all the other points. If in this question I said find the coordinates of the absolute maximum point, the coordinates of the absolute maximum point, that looks like that's the point 2, 2 that's marked there. So when I answered this, the coordinates of the absolute maximum point I said is 2. And then it wants me to find the value of the absolute maximum. That's just the same as doing the value of the local. Here I'm going to say the absolute maximum value is, I might say y equal to 2. I kind of like y as opposed to the function notation, but they're interchangeable. Function notation and y are equivalent to each other. So the absolute maximum is y equal to 2, which occurs when x equals to 2. And then I'm asked to find the coordinates of the absolute minimum point. The coordinates of that point, that's the point 0, negative 2. That might be the challenge, just knowing that points on the y-axis have an x of 0. The coordinates of the absolute maximum are 0, negative 2. The value of the coordinates of the absolute minimum are 0, negative 2. The value of the absolute minimum is the y-coordinate of that point, so I might say the absolute minimum value is y equal to negative 2, which occurs when x equal to 0. I could use the function notation or the y notation. They're interchangeable. It doesn't matter which you pick. I never test on these. Let's just do one and call it done, even though there's two. This is getting deeper and deeper into calculus. The increasing, decreasing local max, local min, that will peek its way into the test. This won't, so I'll just kind of speed through it. So I have a graph in problem 18 that looks remarkably similar to the graph in the example. We have a graph in 17 that doesn't look so simple, so let's do 17. Part A for 17, we need to look at this graph and find the point that's higher than all the points. Hopefully it's readable. This right there is the absolute maximum point, because over this region where the graph is bound on the left edge and the right edge, it doesn't extend. That point 3,4 is higher than any point close to it, so we'll call that the absolute maximum point. The absolute maximum value, I'm just going to say it's y equal to 4. If I gave you a function name, which I didn't here, you could use the function name equal to 4. And I'll say which occurs when x equal to 3. I'll pluck off the x coordinate just like I do for the local maximums and local minimums. Next, I want the lowest point, the absolute minimum. That's this point 8, negative 21. That point 0,4, it's not the lowest point because there's a point lower. That's not the highest point. There's a point higher. It's just a distractor point. The point 8, negative 21 is the absolute minimum point. And if I wanted to write the value of the absolute minimum, since I didn't use a function name, I'm just going to say it's y equal to negative 21, which occurs, and I skip the which occurs, when x equal to 8. That's the end of the chapter. The second part of the video that I did for this section 2.6, neither one of the new concepts, none of the three concepts are on the test. I won't ask you to find a constant interval. I won't ask you to look at a table and say whether it's increasing and decreasing, although that would be free points. And I won't ask you to find an absolute maximum or absolute minimum. Not that it's that hard. It's just that thinking about what I do in college algebra, the local maximums and local minimums I do, the absolute maximums I don't. So I just want to prepare you for college algebra, not so much prepare you for calculus, which this comes in every calculus class. All right, we're ready to work on the practice test, and then we'll take our test over chapter 2.